Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a continuation of graphing using calculus. You should have already watched my videos on the calculus of increasing and decreasing functions. You should have watched my video on the first derivative test and finding local extrema, which was the previous video to this. Or actually, no, there was one other one prior to this, which is the calculus of concavity and the second derivative test. Now we're going to use all of that information to help us graph here. Now, this is not the finalized list of how to accurately graph a function. There is one little exception, and that's this asterisk that you can see right here. The tendency of a function as x goes to plus or minus infinity is a topic reserved for a different section or a different video. But we're going to get as much of our graphing skills kind of solidified at this moment. So here's the major recipe for the most part. You do mathematics in the order you've learned mathematics. So if I give you a function, or if your instructor hands you a function, and they say graph this function using calculus as accurately as possible, the very first thing you should do is recall your elementary algebra. Find the intercepts. If they're easy to find the x and y intercepts. It is often the case, just to be honest, that some intercepts are very difficult, if not impossible to find. You have to know when to give up. So it's for the most part, you should be able to find them, but there are going to be a handful of cases where finding intercepts is going to be far outside of your ability or control. The next thing you're going to do, again, climbing the way you've learned mathematics, you then step into your intermediate algebra and you state the domain. So determine the function's domain. And then, continuing on with your intermediate algebra into pre-calculus, really, you state the vertical asymptotes. And I say this is part of pre-calculus because you're going to determine the behavior of f near those asymptotes, and usually you would use calculus and limits for that. So in this video, we're not going to have any vertical asymptotes. We'll have one that we'll have to deal with, but that's more of an advanced topic, and we'll get to that a little bit later. Next, again, going through algebra and pre-calculus, work with any horizontal asymptotes if you have them. That will usually involve limits as well. And again, as I stated earlier, that is something that you usually need another section's worth of material to kind of really see. You need something called L'Hopital's rule. So after that, you step into calculus. Compute the first derivative, determine the intervals of increase and decrease, use the first derivative test if you can to indicate any local extrema. Then compute the second derivative. Use that to determine the intervals of concavity using a sign chart, state the points of inflection, and use a second derivative test if you couldn't use the first derivative test, which is very rare. And then make sure you organize all that information and then very, 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 very cleanly graph. That's all I have to say. Sloppy graphs at this point are completely unacceptable. And so graphing using calculus tends to be the longest part of calculus just because you're spending so much time doing everything you've ever learned. And that's critical to note. So my students know that I'm a stickler for prerequisites. The reason why is because when you get to this material, everything you've ever learned is pretty much on the table. And so you have to be good with all your prereqs to know how to graph appropriately. So we're back to this problem, and this is the last time I'm doing this problem. So let's accurately graph this curve. Now I'm just going to go through, I'm not going to list out the steps. Instead, I'm just going to go through logically what makes sense to me as far as the order in which we've learned things. So the first thing I'm going to do is state the intercepts. So I'll zoom in here because it's just easier for me to do. And I'll start with the y-intercept. because the y-intercept is really the easiest, right? You let x equal 0. If you let x equal 0 in that, you get 3. And now once I get to this point, I immediately realize I'm going to need a table of values in the long run. So I will actually list a table over here that I will fill out as I move along. So again, we plugged in 0, we got out 3. That's just going to be helpful for us in the long run. The x-intercepts. Well, those occur when y is 0. I don't need to say that because you guys have had plenty of algebra. So we'll let the output be 0 and solve, right? So we're solving 0 is equal to, I'm going to write it as a positive x to the fourth minus 4x squared minus 3. In other words, I multiply both sides by a -1. And I'm going to factor that. That's an x squared. Let's see. Does not factor. Well, that's nice. Well, if it doesn't factor, then you know you're going to have to use the quadratic formula. So using the quadratic formula, I see that x squared should equal, let's see, the opposite of 4 plus or minus square root. Notice you're using your algebra skills, right? Minus 4ac all over 2a. And that would give me 2 plus or minus, let's see, 16 plus 12 is 28. Is that right? Yeah, 28, which is 2 root 7 over 2 or root 7. I should probably double check my mathematics. You don't want to go too far with bad math. If you break something early, everything else falls apart. So always double check your work. So I'm just going to quickly check my work here. Opposite of 4, 4 squared minus 4ac, 12, 28, 4, 7, 2, 2. Yep, that's me, by the way, computing in my brain. All right, so I happen to know right now that these are not my x-intercepts, but that x squared is equal to that. And that will imply that x is equal to plus or minus the square root of 2 plus or minus root 7. Now, let me just stop right here and mention, you need some realism here. 2 minus the square root of 7 is negative. You cannot, when you're graphing only over the real numbers. So this, if I include the negative, is not going to work out. So I'm going to go ahead and cross that out. And I know that now my x-intercepts are plus or minus the square root of 2 plus the square root of 7. So I will write that over here. My x-intercepts are the positive square root of 2 plus root 7 and the negative square root of 2 plus root 7. It's not pretty. I would absolutely agree with that, but it is what it is. I honestly think the hardest part for most students is the fact that they have numbers that are in exact form here, and they're going to have to grab a calculator to approximate those, or they'll have to kind of just use their brains to approximate those values. And that tends to be a frustration, because if I could grab a calculator, then why am I graphing by hand? I totally understand that statement. All right, so the next thing I'm going to do is, let's see, we got the intercepts. I'm going to mention the domain. I'm just thinking about how I learned mathematics. So now I'm going to worry about the domain. So the domain of our function f is all real numbers. So there's no restriction on our domain. The next thing I'm going to go through, well, technically there's something prior to the vertical asymptotes that I skipped, which is our step 3 here. Notice I didn't write something in. That's on purpose because we technically, well, we would need it in this specific problem, but I'm not going to use it right now. I think that's just going to muddy the waters. So for right now, I'll just continue forward without that little extra bit in here. But I am going to mention, are there any vertical asymptotes? Like now I'm really thinking about, okay, now I advanced through my mathematics. Let's see, what else did I learn with graphing? Well, I had asymptotes. So are there vertical asymptotes? Well, if you don't have domain issues, there are no vertical asymptotes. So I'll say none. Horizontal asymptotes. Well, horizontal asymptotes are the behaviors as x goes to plus or minus infinity. And this does not become finite as x goes to plus or minus infinity, so it does not have a horizontal asymptote. I mean, you could double check that. You could always say the limit as x goes to infinity of f of x, and you could totally evaluate that, but it's not actually an easy one, super easy that is, to evaluate. Well, actually kind of is. that would be the limit as x goes to infinity of 3 plus 4x squared minus x to the fourth. You cannot say that's infinity minus infinity, so it's 0, because it's not like that. But you can use a little trick here. This is the same thing as the limit, using limit laws, this is 3 plus the limit as x goes to infinity of 4x squared minus x to the fourth. But I can, and of course that would be infinity minus infinity, but I can actually factor here. That's often what you want to do in these situations. So I can factor an x squared off of both these. And if you do that, you get something approaching infinity times something that's approaching negative infinity. Now I know what that's going to be. That's negative infinite. So that's 3 minus infinity, or in other words, this limit is going to be negative infinity. And in fact, if you do the mathematics the other way with x approaching positive infinity, it'll be negative infinity. It's the same. So the limit as x approaches negative infinity of our function, if you go through all that work, it'll also be a negative infinity. This just gives us the end behavior of our graph. So let's see. I've found my intercepts. I've found the domain. I found out there's no vertical asymptotes. There are no horizontal asymptotes, but I still found the end behavior of the function because that's going to be useful. Now I'm going to go ahead and start stepping into calculus. In the calculus, I'll start by taking the first derivative, and actually I tend to take both derivatives at the same time. So I'll take the first derivative, which is going to be 8x minus 4x cubed. We already did this problem, but I'm still going to redo it all. And the second derivative, which is going to be 8 minus 12x squared. Again, check your work. Be very careful when you do this, because if you make a mistake early on, your graph is just done. There's no saving it. Now you're going to find the critical numbers. The critical numbers of f occur when f prime is 0 or does not exist. So we're going to go ahead and, how do I want to note this? I'll say this implies f prime is equal to 0 when, and then I'll go ahead and solve that. And we did that earlier, but I'll just state it here, x equals 0. Actually I do have to kind of do it off to the side. So I'm going to go ahead and factor off of 4x. We have 2 minus x squared. So that's what it was, plus or minus root 2. Okay. Okay, so when x is 0 and x is plus or minus root 2, so I'll just grab that and move that down here. And let's see, f double prime is 0 when, and again, if you were to solve this right here, you would get 2/3 x equals plus or minus root 2/3. Okay, so I found my first and second derivative. Now what am I going to do? I'm going to make sign charts, and I'm going to plot where these derivatives turn into 0 or where they don't exist. Oops, that's supposed to be equals 0. Right. And I'm going to stack them appropriately one above the other. So let me go ahead and bring in this bad boy right here, and I will just graph this out. And right below it, not too far below, I'm going to graph a second number line, just right below it. And let's see, do I need anything else? Nope, I don't think so. I'm just going to go ahead and turn off my ruler, and I'll plot all those critical numbers. For example, x equals 0 and x equals plus or minus root 2. So I might, well, I'll just do it this way here. I'll say this is x equals 0. And then here's, I'll just say negative root 2. And therefore maybe right about here would be a positive root 2. Those are the critical numbers for f, which is where the first derivative, which I'm going to label right here, turns into 0. And the critical numbers for f prime, in other words, where the second derivative turns into 0, are plus or minus the square root of 2/3, which is probably about right here. Negative root 2/3 and symmetry positive root 2/3. Okay, so all those are critical numbers for the relative or the relevant or respective functions. Now I'm going to do a sign chart, and let's see, f prime. So then you go to f prime and you say, all right, we have 0 plus or minus root 2. Let me test f prime at those values in between. F prime is 8x minus 4x cubed. So let's see. Plugging in 1 to 8x minus 4x cubed. 8x minus 4 is going to be positive. Right? So I'm just going to say f prime of 1 is positive. That's all I really care about. So we get a positive value for the derivative there. F prime at negative 1. Negative 8 plus 4. Yep, it's negative. And then you could test any value below negative root 2 in the derivative again. So I would test like maybe a negative trillion or something like that. And you'll get a positive value for that. So let's put positive here. And you could plug in any number into the derivative that's greater than square root of 2. And for me, I'll just plug in 1 billion, and that will give me a negative, actually, because it's subtracting. Remember, your first derivative, you're subtracting x cubed. So if you plug in 1 billion, you're subtracting a massive number. All right. Well, what does that imply about the function? That implies that the function is increasing on this interval and increasing on this interval, and it's decreasing on that interval and decreasing on that interval. And by the first derivative test, if the derivative switches from increasing to decreasing, we have a local max here. If it goes from decreasing to increasing, we have a local min. If it goes from increasing to decreasing, we have a local max. And that is if your function is continuous, which our function is, so I don't have to really sweat that issue. And since we have those x values, I'll go ahead and plot them over here. Negative root 2. Actually, technically, plus or minus negative root 2 leads to the same value. If you were to plug in a negative root 2 into, or a positive root 2 into your function, you'd get 8 plus 3 is 11, minus 4, which is 7. And we also have 0, which we said was 3, so we have that already plotted. That's going to be a local min. I'll just mention that here. And these both are local maxes. All right. Anything else I need to state? No. Now I'm going to go to the second derivative. And second derivative, I'll do the same thing. I'll test the second derivative at points in those intervals. When I say those intervals, I mean these intervals right here. So I could plug in 0 to the second derivative, and you will find if you did that it would be positive, because the second derivative is 8 minus 12x squared. So it's positive here. And plugging in any number less than negative root 2/3 or greater than positive root 2/3, you will get that the derivative is, the second derivative that is negative. What is the ramification graphically? That wherever the second derivative is negative, it's concave down. Concave down. Wherever your second derivative is positive, your curve should be concave up. And where the second derivative switches signs, as long as your second derivative is continuous, you have an inflection point. So we have an inflection point here and an inflection point there. Again, I just go here and I plot, or I label the plus or minus root 2/3. We actually did the mathematics earlier, so I'm just going to write that in. I think that mathematics was 49/7, but I could be wrong. Maybe it's 47/9. And I was wrong. It was 47/9. So there we go. So we have yet to actually grab a calculator. So that's good. And now I pretty much have everything I need. Oh, by the way, those are inflection points. I pretty much have everything I need to graph. That's all I really truthfully need. I just needed to do all that stuff all the way to Calc 1, including the second derivative. Once I have all that done, I can now graph. And the way I'm going to graph is I'm just going to draw in where my y-axis is, which is where x is equal to 0. So notice how I'm lining it up there. Draw my y-axis in. I'll draw my x-axis. I will start plotting points here. So let me turn off my ruler. And the points I'm going to plot are actually from my table. So I'll plot 0, 3. Now notice, first of all, that the scales that you're going to need to have here, the y values should go all the way from 0 to 7. Yeah, 7 is the largest. I'll probably go for my y values going maybe, I'll have it go from -7 to 7 or something like that. So that's one thing you should note. Also, you should note the x values, which are listed right here, but also we have this x-intercept. Those x values are going to need to be plotted. So we have to kind of approximate those values. That does require a calculator. So unfortunately, that's what I'm going to have to grab right now. So I've grabbed the calculator, I've computed those out, and that's unfortunate because you don't want to have to grab a calculator when you're graphing by hand, but such is life. Now I'll go ahead and plot some points here. So 0, 3, I'll plot that one. So up 1, 2, 3 units. Maybe I'll use blue for my point there. There we go. And let's see, the next one we're going to plot is negative plus or minus 2.155, 0. So those are the x-intercepts. So I'll go back 2 units. So 1, 2, and some change. And forward 1, 2, and some change. It's probably important if you're off grid there. So 0, 3 was on grid, but this is totally not on grid. So it might be good to maybe just label that point. So I will label that point at the end because I don't know where my graph's going to go through, and I want my graph to be able to really hit those values nicely. Oh, and you should also note where I plotted those, I didn't line them up appropriately with my graph. So let me go ahead and align those up with my graph. So let's see if that is considered to be root 2/3. I'm going to say that 2, I'm going to probably say it's over here. I'm looking up above. I'm looking at these where I placed them. So it might have been nice for me to actually have approximated these values prior to that, but I didn't. So I'm going to go ahead and say that if this is the square root of 2, then up above, this will be my, technically it should actually probably be right about here, root 2/3. And likewise on the other side, this will be negative square root of 2, and this will be roughly a negative root 2/3. And square root of 2 is 1.4 and change, and we want to get to 2 point something and change. So I'm gonna go ahead and say right over here is my x-intercept of 2.155. So I'll plot that there, and I'll do the same thing over here. Okay. And now I can go ahead and plot the rest. A plus or minus root 2 and 7. So let's go ahead and climb up 7 units. That was 3, 4, 5, 6, and 7. Try to align this as good as possible. And same thing here. Root 2, 7. Again, graphing is the longest part because you're going to spend some time trying to be accurate. And then now we're going to graph, what is it? 0.816, which is negative root 2/3 and positive root 2/3, comma 47/9. And that's a little bit greater than 5, right? So 5 and change. So 5 and change, so somewhere around here maybe. And similarly, somewhere around there. Okay, so I've got my points plotted. Now, you could just choose some place to start graphing. I usually just start graphing at the y-axis. We have a local minimum at the actual y-axis. Sorry, my hand keeps moving the screen. And we're concave up. So I happen to know it's going to look like this. It's going to be increasing on that interval until it gets to the square root of 2/3, where we're going to get an inflection point. So it'll go from concave up to concave down at that moment. Notice how I try to do that. It's still increasing over this entire interval though. It gets to that local max at the square root of 2 there. And then it becomes a decreasing function at that point, and it's going to remain concave down forever. Decreasing and concave down forever. And we'll zoom out a little bit. Notice it's going to fall forever, and we had mentioned as x goes to positive and negative infinity that the y values dip down to negative infinity. And now I'll graph to the left. It's concave up, and the function is decreasing. This kind of throws people off because you're drawing to the left, but it's actually concave up and decreasing, so it's decreasing like that. You're drawing to the left, a lot of people visualize that they're increasing, but it's actually decreasing. Then it switches to concave down. This is an inflection point, so it switches to concave down. It's still decreasing though. There we go. And then it switches to increasing, but remains concave down. So increasing but concave down forever. And that is a very accurate graph of that function, using all the steps provided in the previous screen right there. So it is a really accurate way of graphing using calculus. Now, rather than stick another 4 graph problems into this video, I'm going to break them apart. So this will be part 1, and then the next video, next example will be part 2, and so on and so forth. So I'll see you in the next video.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.